All right, we are starting the circulatory system, which is one of my favorites. So let's go ahead and get started. So I love the circulatory system, and I've worked in cardiology for a long time. But one thing that I learned way back when was from a doctor who said, you know, the heart's just like an old house. You have your walls, you have your electricity, and you have your plumbing. And so that's exactly how we're going to talk about it. So the first thing we're going to talk about is just the anatomy and blood flow. And let's do that by taking it up to the whiteboard. So let's go ahead and check this out. So you have your right atrium, your right ventricle, your left atrium, and your left ventricle. Now, what we need to start talking about then is a little bit of plumbing. So let's go through this. So what happens when blood comes into the heart? It comes in through the vena cava. Now, is this an artery or a vein? It's a vein. Anything that's coming into the heart is considered a vein. Any vessel leaving the heart is considered an artery. So let's go ahead and talk about where this blood flows. So blood comes in the vena cava and it's deoxygenated. It has literally spent all its oxygens giving muscles and tissues the oxygen it needs, and it is coming back for a reload. So it goes through the right atrium into the right ventricle. It does this through the tricuspid valve. Now it's going to go through the pulmonary valve and go through the pulmonary arteries. Now, are these oxygenated or deoxygenated? Right, these are still deoxygenated. The pulmonary arteries are the only deoxygenated arteries in the body. So here it goes to the lungs, it gets all oxygenated, and it comes back into the left atrium through the pulmonary veins. Now, are these veins oxygenated or deoxygenated? Right, they are oxygenated. These are the only oxygenated veins in the body. So it comes into the left atrium and then goes down through the mitral valve into the left ventricle. From the left ventricle then, it's going to go through the aortic valve, through the aorta, and to the rest of the body. So now that we know how blood flows, or it's just a good reminder of the anatomy of the heart, we need to talk about just how it contracts. Well, this is an important part because this is where we get into systole and diastole. So when blood flows through the heart, it's not each chamber beating at a different time, like you kind of would see it in that picture. But basically, the top part of the heart contracts and the bottom part of the heart contracts. When the bottom part of the heart contracts, that is called systole. So systole, everybody, if you want to write off to the side, systole is contraction of the ventricles. Now, that is a huge muscle, and when it does that, it pushes blood out into the aorta through the body and into the lungs, all right? So high pressure system. When those ventricles, after they're done pumping blood out and contracting, then they start to relax. Relaxation of the ventricles is called diastole, all right? Write that off to the side. Relaxation of the ventricles is called diastole. Now, what's so cool about that, if you think about it, is that would be systole over diastole, right? Which also makes sense why systole on a blood pressure reading is high, because that's contraction. It's forceful blood going through the body. That lower number, when you start to hear it fall off when you're taking a blood pressure reading, that's because it's relaxation, where the blood stops that high pressure system of blood flow through the same vessels, okay? So that's systole over diastole. That's good old 140 over 90, all right? Which again is what? It's our number for hypertension. Now, if we're gonna go ahead and move on, you can actually see diastole and systole on a chart. And I'm gonna call that the mechanics of our cardiac cycle. So let's go ahead and look at that on the whiteboard as well, because I think it'll give us a good picture to some opening and closing of the valves, as well as the contraction and relaxation of the ventricles. So let's go ahead and take a look at it. So take a look at this figure. So what you see here is on the x-axis we have volume, and on the y-axis we have pressure. So you see on the bottom there's ventricular filling. What is that called again? Right, diastasis. And then all of a sudden there's no more volume increase, but high pressure increase. And then it says isovolumic contraction. What that's stating is after the blood has filled the bottom part of the heart, the ventricles, this isovolumic contraction with no volume change means that the heart is getting ready for a forceful contraction. It's building up, but it can't go anywhere yet because the valves are closed. Then all of a sudden those valves open and you see an increase and a significant decrease in volume, but the pressure stays the same. That is ventricular ejection or systole, okay? So during this time then, all of a sudden you see pressure decreasing, and again, no pressure changes. That's called isovolumic relaxation. So this is again when all the valves are closed and the ventricles are relaxing, getting ready to be filled again. So on that graph, you could also see where the valves closed and where they open. Now, there's never a time when all the valves are open at the same time. But one thing that's really cool is that when you hear that lub-dub of the heart, those are actually closing of the valves. All right, so when we talk about heart sounds, there's 4 heart sounds. We call them S1, 2, 3, and 4. Now S1, that is our first heart sound, the lub, if you will, and that's closing of the mitral and tricuspid valves, okay, MT. MT, the second one then is closing of the aortic and pulmonary valves, so AP. So you can remember, try my apple pie if you want to remember how those two go together, okay? Try my first heart sound, apple pie, second heart sound, all right? S3 and S4, those we think about heart sounds that shouldn't be there. So like an S4 heart sound, for example, people with congestive heart failure have that, all right? So those are not normal, but S1, S2, those are normal in a patient, and you need to know what valves close to hear those sounds, all right? Good. Okay, so we've talked about the walls and kind of the plumbing of the house, so now we're going to talk about electricity. And let's go ahead and check this out on the whiteboard. All right, so look at this heart. One thing that's pretty cool about the heart is that it has its own electrical source called the SA node. And the SA node is what we consider to be the pacemaker of the heart. And it can self-generate action potentials, which then is going to spread to other cells. So the SA node is going to fire between 60 and 100 beats per minute. That is what a normal pulse should be. Anything below 60 is bradycardia, anything above 100 is tachycardia. Now, if we look at the SA node, it is going to generate its own action potential, and then it's going to spread it through the atrium to the AV node. The AV node also has slow action potentials, and so it gathers up the electric potentials, and when it's ready, sends more electricity down through the bundle of His and then up through the ventricles. The AV node is important because we need time there to allow blood to fully fill the ventricles, and then it needs to spread down the middle of the heart so that contraction can start at the base of the heart to allow for uniform contraction of the ventricles, allowing blood to get out of the pulmonary and aortic valves. We can also see this then on an EKG. So let's take a look at that. So if you look at an EKG, there's all these different waves, which can be slightly unfamiliar, but let's take a look at them and put them with what's going on in the heart. So if you look at the P wave, it's this little area of depolarization. Remember, if you have a depolarization, you have a contraction. That's how muscles work. So look at that little P wave. That is actually atrial depolarization. So that's what's going on between the SA node and the AV node. And then you see that pause. Well, what's that pause for? That's that AV node getting up all its electricity to send it out to the ventricles. Now you have this huge QRS complex. And what is that? Well, the QRS complex is basically ventricular depolarization or contraction, right? And look how it's in this whole thing of systole. So this is systole or ventricular contraction. And then it goes back to baseline, and there's this little T wave that's actually pretty important in medicine. All I want you guys to know about it, though, is it's just this extra little relaxation of the ventricles that we can see on the EKG. So now you can read an EKG, but I would definitely know, in all seriousness, what the different upstrokes are, what's happening in contraction, and what a P wave means in the QRS complex, okay? All right, good job. So last little thing, and then we're going to be done. A couple things here is the rest of this kind of area talks about fast action potentials and slow action potentials. One thing I want you to know about the difference of them is that fast action potentials in the heart are all over the heart, except for the SA and the AV node, which we talked about when we were talking on the whiteboard, right? So when you think about the SA and AV mode, those are slow myocardial action potentials, and the big player there is calcium. Calcium, these slow gated calcium channels, allows calcium in in out of the cell, but they are not bothered by any of the fast twitch myocardial cells around them, and they do not have anything to do with potassium or sodium. All right, you can go ahead and read through those sections, but otherwise this is a perfect time to take a time out, look at a few questions, and then when we get back, we're going to talk about blood pressure and hemodynamics.